that. Then just to be quick, normally I was supposed to just go like that and create some form of handle, just a quick sketch. Huh? Is it like that? Something like that, right? Maybe I'm forgetting how the diagram was. Then from there, it will be like that.
It's like a voice.
Yeah, just a minute. I'm trying to draw our camera here. Okay, so we've got the following problem. So it's something like that. So the problem has been given with an axis which is Z, which is X, and which is Y. So this, we've been given known forces to say there's a force that's acting, of course, in which direction it's parallel to the X. So we know that this is F of X, which is equals to 250 newtons. Then at this point, so it's at that point, at this point, we've been given a force that's acting as F. Of course, it's parallel to the Z, so it's in the Z direction, which is equals to 100 newtons. Then we've also been given another force, which is acting in the Y direction, which is Fy, and Fy has been given as 75 newtons. So this is the problem that has been given. So the first thing we are asked to do is draw your FBD. So drawing the FBD is quite easy. The first thing you can do is you identify all known forces. So you identify all your known forces and draw references at those points. So you draw references at those points. So the known forces, in this case, we've got Fx. So at this, you draw a reference. What reference are you going to use? The same that you've been given. So it means upwards is my Z positive. In this direction, I'll have my Y positive, and in the other direction, I'll have my X positive. So the same will happen here. I'll have my Z positive, and in this direction, I'll have my Y positive, and in this direction, I'll have my X positive. So this will help me eventually. Then from there, you repeat the process, but this time you must identify all supports. Eventually, what we're talking about is support reactions. So we have to identify all the support reactions. So you check, what supports do I have? We don't have any supports here, but we have a wall. And as drilling occurs, what will happen with this wall? So a wall is usually a fixed end. The end is fixed. So it means we've got a fixed support. And the nature of a fixed support is that all directions, your displacements are what? Restrained, or they're not permitted. Hence, you have reactions in the sense of, as I drill, if I try to apply, that's the drill, it's moving. When I try to move up, what's happening? Because when you're drilling, you've got a tendency, sometimes you might apply a force, you might want the drill to be pushed up. What happens? There'll be a reaction. So that reaction is what we say that at this point I will have, we use the positive sense of definition. So we'll say at O we will eventually have OZ in the positive direction, and the same thing will apply in the Y direction. This will be OX, and the same thing will apply in your OY direction. So you have all your reactions. So the reactions are quite easy to identify. The reactions are quite easy to identify. So you go back to the problem that we did in lecture 2, you also draw a comparison, because the unique part with that problem is, imagine the same problem, imagine this, and instead of me giving you these values, I put maybe a pin support here, because that other problem they had put a roller and a pin support here. So in this case, you've been given these values already, and you're only asked to evaluate this. So meaning the problem that you're given as a homework is actually more complex. This one is much easier. So the only challenge always comes with the moments, because the reactions, everyone is comfortable. So how do we visualize our moments? So when it comes to the moments, so we come to draw the moments. So for the moments, by definition, we say a moment is what? From a pivot, a given pivot or point of action to where a force is applied, where we've got our line of action. So it's our line of action, and we're having our force. From this point, given a distance, a moment is defined to be that distance multiplied by the force, or force times distance, others would say. But I prefer writing it in this because when we apply vectors, we need this multiplication sign and we need this order because this is not equals to F. These two are not equal. Always remember that. So what we do is, this is a distance and I'm applying a force. So what's happening? There's a rotation. So a rotation will be, the rotation is around which axis? This black pen, right? So it means if I've got this was X, and I say in this direction, this was, let's say, Y. Then I say I applied a force and this distance in the X. What will happen? Where is the rotation going to be? It's going to be around the Y. So meaning my moment M-O-Y. M-O-Y depends on a distance and a force, and this force is being applied in which? Z, right? And this is what? Dx, right? So meaning my moment MOY depends on a distance in dx, but a force being applied where? Fz. So this is where the imagination comes from. Yeah, I think we were able to show that you can actually have formulas for all of them. You can have formulas for all of them. So when you're solving a problem, you'll be able to deduce some formulas that you can use. But the first part is you have to be able to imagine because you need to explain to others. You can't explain to others just using formulas directly. So we'll try and apply this concept. So what we'll do is we'll come and say the first thing is we have, so our free body diagram, we've identified that this is how it is. So we'll just indicate to say, since this is my axis, I'll say this is my axis. So around, I'll have a positive moment. So what I'll do is, I'll indicate to say around in that direction, I'm having M, O, Y. And I can draw a dotted line just to indicate that, yes, it can be eventually a moment in that direction. So around here, I also have, since this is my Z, so I'll get this as my axis, then I'll be moving in that manner. So around here, I'll have my M, O, Z, and I can draw a dotted line to say eventually it can also be the other direction. Then here, this is my axis. I'll do that. I'll have my M, O, X. Eventually, I can have it in that direction also. So this is how my free body diagram is going to look like. So I have that. My free body diagram is done. Now, when your free body diagram is done, of course, your step 2, so this was actually your step 1. Your step 2, you have to apply your equations of equilibrium. So the application of the equations of equilibrium is because we are in a problem which is known as statically determinant, meaning the number of unknowns is equal to the number of equations. So in this case, we've got how many equations? 6 equations. And we've got how many unknowns? We've got 1, 2, 3, 4, 5, 6. So you deal with statically indeterminate problems later on, but most of your problems are already statically determinant. So So we have this. So the first thing we do is sum of forces in the x direction equals to 0. Sum of forces in the y direction equals to 0. Sum of forces in the z direction equals to 0. X positive is in this direction, so I can indicate this is my x positive. My y positive is in this direction, so I can indicate this is my y positive, and this is my z positive. So if I compute this in the x direction at point O, what do I have? I've got OX. It's in which direction? The positive direction, so I have positive OX. Do I have anything else? No. At this point, I have no force, but I have a force at this point, and this force is also in the what? X direction. So I indicated, but in which side of the X direction? Then there it's pointing this other direction. This is the positive, so it's in the negative. So it will be minus 250 newtons. Do we have anything in X here? No. So this will be equals to 0. So it gives you that OX is equals to 250 newtons. So meaning at OX, the reaction has to be 250 newtons for this to be in equilibrium. So that's okay. Same principle, same principle. Now let's solve something with the moment. Oh, the papers are finished. Okay, we'll solve it here. Now let's look at the moment situation. So the moment situation is the most tricky one. For example, let's say the sum of moments in the OX direction, and we said for the OY direction, this is what? If we imagine the axis, this is our positive. Okay. So the question is, if this is my Y, and this is point O, and I can draw my other axis to try and visualize what's happening, what will cause a rotation around this, or the rotation might be like that? So that would be the question. Oh, we already did it here, right? We saw that it is a force in this direction. So meaning here, if I imagine, because this is my rotation, it's rotating in this direction. So since it's rotating in this direction, it means if I have a force like that and a perpendicular distance of something like that, what will happen? It will eventually cause a rotation. So if I apply what we do with moments, like for example, we said we had an example where there was a wall which was fixed, then we had a force, right? We said at this wall, we try to evaluate the moment at MO. We said at this point O, we have to draw straight lines. These lines are passing through our point of action, and where they intersect the line of action, meaning where your force is being applied, at that intersection, they form a 90 degrees, so we can evaluate the what is it called again? The moment. So it's the same principle that will be applied here. So here we've got a force in this direction. We've also got a force in this direction, but this force and this point are parallel to each other, meaning there won't be a moment produced. Because this force at this point can be translated to this point. That's the advantage of moments, is that you can get this, because it's a vector, you put it here, it's the same force. And you find that there's no distance, so it equals to 0. Then we've got another force here. This other force, if you notice, it's got this distance here until this force. So if I say D, this was my DFZ, right? And this was my DY. You notice that these ones, it's got its distance and it's got that, it forms your 90 degrees. When I'm at this point, it will turn, but cause a rotation around what? MOX. So for your MOX, it's evident that you have your dy multiplied by your FZ. Then for this one, it's going in that direction. So it's moving in this direction. I have this as my y. Since my force is moving in that direction, my force is applied here. Since it's a vector, I can bring it to point O. And it's also got a vertical distance. So it tells me to say this force, I can also bring it to, this is my Z, so I can bring it here and say this is also my Fx, it's a vector, which is equals to 250. And the distance always remains the same. So I can translate the distance to this point, I translate it to here, it will give me this distance, which was given as, what was the distance? Huh?
25.
225 millimeters, which is the same as 0.225 meters. So, meaning if you apply the sum of moments, this will eventually give us MOX, which has been defined, not MY, which has been defined as positive in which direction? In this direction, right? Then the other one, let me just check, because this is coming. So it's this direction that's positive. Then the other one is going the opposite direction. So it will be minus the distance, which is 0.225, multiplied by your force, which is 250, equals to 0. So MOX, or Y, I mean, will be equals to, this times this, what does it give?
56.25.
So 56.45 newtons to 2 decimal places meters. So that will be the answer. So you have to apply the same principle to find this. And we've already evaluated the other one. It will just follow that. So you apply the same principle. And from there, you are done. So please, it needs you to practice again and practice also on the other question and see that the principle applies. Then what you can do is, you've seen these formulas we're coming up with. Try and apply them on different problems and see if you get the same answer. If they work on 5 problems, meaning just master them, because what you do is such things. You get your X, Y, and you get your Z. Then you say, okay, here it's saying the moment of X is equals to, I circle my X, it will just be this times this. So you say, so if it's this, it will give me just Y, Z. You put your D and you put your F. Then you say, how about if it's X, Y, and Z, and I'm looking for MY. So you say, okay, for MY, what is it going to give me? Is it going to be this times this? If it's this times this, it will be just your dx times fz. Then how about if it's this? You've seen the logic. Such things, that's what we expect you to eventually do. Because it makes you faster in an exam, of course. So that's me personally in university. When I solve such a thing, yes, I explain, but in an exam, I'll just write my formulas and say, okay, the logic is this. So I have this, I draw my free body diagram. Quickly, I have my formulas, I solve. And I'm done. So instead of spending 20 minutes, I'm done in 5 minutes. And everyone is asking why. Like, what thought? We have to think. If you've got another method which works, please use it. Me, I'm free. I want to see innovation. It's not that because I showed you only this is the only thing you use. No. This is statics, it's physics, it's mathematics. So we're open to innovation as long as you get the same answer. Okay.
Sir,
Yes.
how many moments are active in this force?
Huh?
How many moments are active in this force?
No, this force produces a moment at this point. Yes. Then we can also calculate the moment at this point. You should try it. You should try it. Because the moment is the force times a distance, meaning a distance and a force will produce a moment. So meaning if I say at this point, is there a moment, what will happen is I'll have to know the forces which have been given, then I evaluate with the distances to check if there's a moment that's acting there. It also takes some imagination, but it's the same principle. It's the same principle.